things. I would say some of them are like he's a co-author of the book in Bayesian statistics, and he recently published another books with some co-authors on that is called Regression and Other Stories, and this is a book that I really love. I got it recently, and I really enjoyed that book. So I encourage all of you to have a look to it. So he's also one of the main contributors to Stan. So it's really a pleasure having Aki today with us and to learn from what he is going to tell us. So I leave it to you, Aki.
Thank you, Javier, for the introduction. I think it was 2 days ago I did send also this title, Challenges in Building Widely Applicable GP Software, but Javier missed that email, and so you were kept in tension until the last moment what I'm going to talk. And so this is based on kind of my experience in different GP software and developing these methods for GP inference. So about my background related to Gaussian processes is that in 1990s, I had studied neural networks, and I did my master's thesis on neural networks. But then from Chris Bishop's book mentioned about Bayesian methods, and it was very lucky and great that there happened to be already software I could just try. So flexible Bayesian methods, FBM by Radford Neal, NetLab by Bishop and Nabney, and kind of could just test that, okay, how well Bayesian inference works for neural networks, and then that works much better than just optimization and early stopping and things like that. So I was then just wanted then to figure out why Bayesian approaches work better, and started studying that more. But then Radford Neal and Chris Williams and others had these connections also then between Bayesian neural networks and Gaussian processes. And again, it was great that the software made it very easy to test also with GPs, and then noticed that, oh, actually the inference is more stable with GPs than with neural networks. FBM was written in C++, and then had a command line interface, and then NetLab was in MATLAB, and we were using at that time also MATLAB, and then I started then based on the kind of the structure of NetLab, started then developing new GP software package we then ended up calling GP stuff, works in MATLAB and Octave. At that time, Python and R, and they were not that well developed, so quite many machine learning people were using MATLAB, and Julia had not even been started. And then it was part of that developing this software for some applications, but then also we developed a lot of the methods and approximate inference, model selection, and so on. And we published a lot of this and kept adding these features to GP stuff, so that not just having standalone proof of concept code, but adding everything to GP stuff for easier use. And then, of course, now So I've now stopped developing GP stuff because it's in MATLAB, and there's not many people using MATLAB anymore, although we still see that people are working as GP stuff, and we are getting sometimes questions. So there are some people at least still using it. And Jarno Vanhatalo, who did a lot of coding for GP stuff in the beginning, is also using it for some projects. And then I'm now part of STAN development team, which is a probabilistic programming framework. So includes language, auditive inference engine, interfaces in R and Python and Julia and command line and so on, and a lot of packages around it. And then based on these experiences on developing different software, and also then reading about other software and reading a lot of papers by others on GPs, then this talk is kind of going through then why it is then so difficult to develop Gaussian process software that would be very flexible and at the same time also fast. So in a STAN, the Gaussian process support is not a priority. It will get eventually better, and in a way that I have hoped that the support would get better faster. But since there are so many different things that are useful, there's always the kind of prioritization what to add and when having limited resources. But there's some things coming along. I'll come back to in the end of the talk. And then to give a bit of idea of kind of the flexibility of using Gaussian processes and like why this kind of flexibility is needed. Some applications where I've been involved. This predicting concrete quality was one of the first. Actually very kind of typical, just non-parametric, non-linear regression. So having measurements of sand material used, like taking photo of the sand grains and measuring elongation and how sharp corners they have and so on, and then knowing what kind of mixture of different sand is used and how much cement and so on, and the recipe. Then we would like to predict, for example, what is the compressive strength of dried concrete in the end, so that we would know, for example, that the bridge will really stay up. And the important goal here was also that previously, when making concrete, a lot of natural sand was used, routed by ice age. It has very good properties, but then it's a limited resource, and there was a need to use more artificially crushed sand. And then with this project, it was possible then to make recommendations to reduce amount of natural sand from 50% to less than 15%. And then this company involved, when using the model to specifically tune recipes, could get even lower proportions of natural sand. But specifically, the model was very kind of plain GP regression, bit of heteroscedastic noise, variable selection, but something that you could do with many existing packages nowadays. Spatial epidemiology, challenge was there then that there are both long-range variations and then short-range variations, and then also background information about this population and population density and so on. And these happen to be challenging that when you are combining different correlation length scales, these are challenging for these approximations. Cancer recurrence risk prediction, there's censoring going on, so we don't know exact values for everything. In this case, there was also the kind of the unknown, this Hazard curve shape model then with GP, and so the observation model is clearly more complicated than just Gaussian model or IID exponential family observation model. Finding minimum energy paths and saddle points. Here's an example of with the gray, there's surface of ice, and then this red and white, it's like water molecule, and how it's then hopping on the surface, and what is that minimum energy path there, and what is that saddle point? So what is the that energy barrier there? How much energy it's needed to that it changes location? And then it's possible to run then this computationally intensive quantum equation computations, iterative computation, and then to reduce the amount of computation needed, we use then Gaussian processes to model these energy surfaces. So this example is not that water on ice, but hydrogen on top of copper. And you can see here in the first figure, so that we already know 2 minima, and then the white points along there are initial points, and we are estimating both the energy but also forces. So these quantum computations give also what is the force affecting, and these forces are then gradients. And so we have observation model which is both function values and gradients in multidimensional space. And then based on having these initial measurements, we can then decide where we need to make more measurements, and then these white points illustrate the path. So that eventually then converges to form the minimum energy path. And then in the end, it is possible then to also try, when we know the path has stabilized, we can also then search accurate location of the saddle point. ABC, or likelihood-free inference, where we want to make posterior approximations, and then again we want to run the simulator only as few times as possible, and with different parameter values here, θ1 and θ2 on y-axis. Crosses are initial points, dots additional evaluation points where we run the simulator, and the red ones are 2 last batches of the evaluation points, and then you can see the equidensity contours modeling the posterior. And then again, challenges in the how we then, based on this Gaussian process model, how do we decide what is this acquisition function so that we minimize the uncertainty in the posterior distribution estimate. And the last example I mentioned, applications, medicine dosage design. So this immunosuppressant used after organ transplants. And then we want to have certain concentration in the body in certain intervals. And then we can model these with ordinal differential equation models. And they are that good models that we need to have observations only in these red circle points. So when injecting drug, and we can learn then how long the drug stays in the body, and or the drug goes first to gut, from gut to blood, from blood to that interesting organ, and then from there back to blood, and then kidney removes the drug eventually, and then we need to give a new dosage. Experiments with made with adults, learning these ODE model parameters, and then also taking into account the weight of these adults, which affects then these ODE model parameters also. And then the interest was that, okay, now we want to use this drug also for children, but we can't make drug studies so easily with children, but then this drug was used in cases where these children had organ transplant anyway. And so there were small amount of data available, and we can use then the model made for adults and extrapolate to children. But children are not just small adults, so it's not enough that we take into account the weight. So the kidney matters with age. So small kids, the kidney is not as efficient removing the drug, and we need to adjust that smaller doses are needed. And then we don't know the shape of this maturation curve. So here you can see there's age going from 0 to 5 years in this example. And then we want to learn something nonlinear, but also monotonic. So again, we can then add that additional constraint that it has to be monotonic curve. So it is maturing all the time, but we don't know how fast it matures in different age before, of course, we get these observations. Okay, so now you could see that it was only the first example, which was just plain regression, and then all the time more elaborate models and combinations with other models. And this brings the question about the flexibility of these different softwares. Some other software, so GPML is started as a companion to Gaussian Processes for Machine Learning book by Williams and Rasmussen and Williams, and initially just the very brief demo code for the book, and then eventually extended to be a bit more complex. GPy, you have been presented. I had to talk about GPy and GPflow, GPtorch, kind of ancestors of GPy. PyMC3 and TensorFlow probabilities, Pyro, Turing are probabilistic programming frameworks in general. So in the kind of belonging to the same group as Dan. And so the first 4 ones are clearly specific to Gaussian processes. And they are going to have the limit aiming for the efficiency. Well, GPML is more like demonstration of proof of concept things, and then these three others are aiming also for high efficiency, but limited to that the Gaussian process part is there, the important. And then the generic probabilistic programming frameworks are more on the flexibility, and then are not necessarily then aiming for the being the best or specifically for Gaussian processes. In law, it's both software and algorithm, and it's not that often used for Gaussian processes, but it also supports certain Gaussian processes which are then actually turned to Markov random fields for inference. MGCV is very common package in R, and there are other packages also which are mainly for splines, but then there's a connection between splice and Gaussian processes, and many splines are Gaussian processes, and certain Gaussian processes can be presented as splines. So it's also good to remember that that's connection. So then I had there kind of three groups of software. So there were these GP specific software, and then probabilistic programming language framework, and then inline MGCV were examples of efficient for certain type of things, and which can present also certain type of GPs. Getting my drawing tablet to wake up. Okay. And if you think about flexibility and speed, so increasing flexibility of the software. So what kind of models we can make, what kind of applications it is useful. And then we have speed. It's quite likely that these different software, they go something like this, that with more flexibility, there's less speed. And it's really, really difficult to have both speed and flexibility. Or it is a lot of work kind of combining these different ideas needed in different parts. And of course, it is also then possible to have demo code that would be not flexible and not fast. But somehow these are the kind of that we have software that are pushing speed up, trying to stay kind of in the limited range, and these can be used. There's of course there's a lot of useful models still, even if staying limited. More flexibility, there's then possibility that pushing, or even it might be that not getting more speed, but more flexibility, but of course they try to also push more speed. And then why it is then so difficult to go that there would be one software that would be great for everything. So you know that the direct implementation for Gaussian observation model, GP for the latent values, cubic scaling. And so if we have bigger data, we want to do something that it's faster. but there's no just one algorithm which would again be the fastest for everything. In low dimensions, there are the specific things like in 1D equispaced grid, we have circular covariance matrix and can use FFT, get ON, log N speed, Kalman filtering, smoothing approaches, ON time. There are these demonstrations going to millions of observations, and like Arno Solin has this real-time app in his mobile phone with streaming data, so infinite amount of data, as long as he just keep shaking his mobile phone and getting accelerometer data and GP is fitting there. Using basis functions approach, so this is strongly now connected to splines, and there's also some connection to inducing points. But then specifically for the basis functions approach, it's they don't scale well with the number of dimensions. So even 4 dimensions it starts to be a stretch. Most commonly 1 or 2 dimensions are used, and this is also something that, like I mentioned, the MGCV package for splines, and it works with this 1 and 2 dimensions. Arno Solin, Simo Särkkä have done, and James Hensman have done some interesting work for the basis function approximations for GPs, and we've also used them in STAN. And Kronecker products, so that in certain cases we can combine one-dimensional covariance covariance matrices for individual dimensions as a Kronecker product, and there are some like nice illustrations of the speed up, but then it's again restricted that like what kind of observation model can be used, and it's restricted that kind of the location of the observations has to have also that like Kronecker structure, so that you, if we think about like a spatiotemporal model with the Kronecker, then you would need to have in every time point all the same spatial locations. And then it means that it's actually not that commonly used, even if it sounds like a nice idea. One of my students also did spend time trying to get benefit from that, and in the end we learned that it's not actually that good. Compact covariance function and sparse matrices. So for the sparse matrices, all these operations, if it's sparse enough, we can make these much lower. And then sometimes it's possible that we have actually non-compact covariance function, so the correlation goes to infinity. But if we present it as approximate these Gaussian processes as Markov fields, we can present as a sparse with the sparse precision matrices and get again lower computational cost. But these are also something that work best only in low dimensions. There are also many great local hierarchical covariance approximations that work well in low dimensions. And inducing point approaches, I'm certain you have these in the summer school part. scale better to higher dimensions, but assume then the functions are actually most often very smooth. Of course, they are like in lower dimensions, you can have more inducing points where there are faster changes, but the idea is kind of that anyway, with these inducing points, that the small number of points, if they can present it, it has to be somewhat smooth. And so then which approximation to use depends on these different assumptions on stationarity, relative correlation, and combination of covariance functions. And so you can't make software that would use just one approach and that would beat every other approach in speed. And then if you want to be fastest in different cases, you would need to implement them all. And that's a lot of work. You have also now had talks on making inference. Full joint posterior has difficult geometry, which means MCMs is likely to be slow. Distributional approximations are likely to be bad. So specifically, when we are talking about the full joint, so if we have the F having GP with some covariance that has some parameters x prime theta, and then the full joint of F and theta, and then even we have something like y is actually some non-Gaussian distribution with parameters f and phi, so the joint also with phi. These are likely to have like these funnel shapes, so it's not well approximated, for example, with Gaussian, and actually these are likely to be even more complicated than just simple funnel jointly. And there are a lot of correlations. So MCMs is likely to be slow, distributional approximation likely to be bad. So that's why it's been common then to integrate out the latent values with something else than MCMC. So just the conditional distribution is usually easier. And you had a talk about EP and variational approaches, Laplace being another one. And then these have then limitations that they are easy to make for exponential family observation models and IID, and then get more and more complicated when going to more elaborate, and I'll say more about that in the next slide. Very common in these GP-specific software is that there's a big data and then just maximizing the marginal likelihood. So finding just the theta hat, phi hat, instead of integrating over that. And it's fine if there's enough data. And there are also ways then to integrate over, but then it gets again complicated, additional support needed. Yeah, so exponential family is easy. They are, when we are using the usual link functions, the likelihood in that parameterization is smooth, often close to normal or flat, and combined with normal prior from GP, the conditional posterior is close to normal and easily handled. Non-exponential family, varyingly difficult. we get multimodalities, we get more kind of the more quickly varying shapes in likelihood. We get more complicated when the observation model can depend on multiple latent values. For example, if we have input-dependent noise model, so that even if it's a normal observation model, but we have a latent GP both for location and scale parameter, or if we have censoring, so the observation model can depend on multiple observations in a way that can be that we need to actually present different observations with different model, multi-outputs, derivative observations, and adding more and more things like this. Again, what was easy and fast gets complicated. The earlier methods get fragile, and you need to think more if you do approximations. And then we get the combinatorial explosion if all these features need to work together. So we had these different possibilities. The approximate computation related to covariance matrix, like using Kalman filtering or basis functions, inducing points, sparse matrices, approximate integration, MCMC, Laplace, EP, variational, latent or joint, different observation models, different priors. And then maybe we want to combine these with other models, like in the drug dosage problem. We had ordinal differential equation model for that. For the drug dosage, the concentration of the drug in the organ was modeled with ODE, but then we just want to include that maturation effect when combining the adult model to children data. And that's why there is no software that would be then both fast and very flexible. It's possible in theory, but it would require a lot of resources. And it's also quite sensible then that these different software packages are actually then specializing for some direction. But it also means that sometimes you need to, like when you are applying, that you may need to think which package to use. And you might sometimes end up in a situation that the simpler model you can make with one package is very fast, but then you would really, really like to have a slightly more complex model. And with that package, you can't make it. And when you switch to more flexible package, it's suddenly really, really slow. And then the question is what to do. So for the flexibility, how about these Turing complete probabilistic programming languages, autodiff, automatic inference, like Stan? One thing is that speed in autodiff systems is not automatic. It's I think that this is something that quite many don't realize, that how much work goes in different packages to make autodiff fast. It's again the trade-off between flexibility and speed. So one thing is that, like Stan project started with autodiff that can do the autodiffing through C++, and it still has that. So it can autodiff through C++. So if you put there in any algorithms implemented in C++, you get autodiff. But it means also that it's in the initial phase, it was really autodiffing through code that is doing matrix multiplication. It was auto-diffing through code doing ODE solving. And these things, especially when there are iterative algorithms, they get slow. The auto-diff tree is going to be big. Yeah, it can do it, but you can get also much faster auto-diff if you then, instead of auto-diffing through the original algorithm, you take into account that, oh, there are actually equations how matrix derivatives work, how ODE solvers, that the solver ends up in a fixed point, and you don't need to actually know what were the iterative steps, and you just need to know what is the end result, or you can make it also faster by taking into account storing some intermediate computations. There's a difference whether you do differentiation in forward direction or reverse direction, and in some cases you want to do it even mixed, some part in forward and part reverse, which all these mean that how you can reduce the size of the auto-diff tree. Also the adjoints, sensitivities and things like that, that what you can do when you are running the original computation, what you can compute at the same time, how do you can combine different rules. And then again, this is a lot of work to add all possible known tricks. And so even if they are called auto-diff, there's a lot of manual work, including making them fast. And then automatic inference, it's also very difficult to make accurate, robust, fast inference. One thing is the computational cost of single marginal likelihood. So these depend also then, for example, of the auto-diff speed, and then in case of GPs, that what is your approximation for computing marginal likelihood or the joint density, and then in additionally difficult posterior geometries require more density evaluations, and then there are the issues whether we have so simple posterior that we could maximize instead of integrating, and then like black box variational inference is often advertised as fast and easy to use, but it's not actually very accurate. And in these applications like these medicine safe dosage system, accuracy is very important. Then, as an illustration of kind of things that what specifically is going on STAN, and I can comment also other software packages that kind of what are their limitations, but then not knowing what the developers are thinking where they could go. So I just mentioned now on STAN that in STAN there's no built-in support for inducing points or using variational inference to integrate the latent values out. There is the joint, so we could use black box variational inference ADVI to integrate jointly, but then that black box BI, as I mentioned, is not actually very good. So we are recommending MCMC to reduce the speed of not having the cubic scaling as usual for GPs. We recommend using basis functions in lower dimensional problems, and of course then if it's additive we can have more, but then the interactions is up to 2 or 3 dimensional interactions. Kalman filtering smoothing exists. There are demonstrations of that, but it's slow without explicit derivatives. So again, order-diff through the iterative algorithm is not fast and would need someone to add built-in things. Oh, there's actually, I remember there is one limited implementation related to that. For small data, covariance matrix approach with just using Koleski and having the cubic, it's feasible. But even then, for example, combining different covariance functions, adding together different covariance functions and making products, it gets to the current, like how the current order-diff is implemented in Stan, it gets slow. So the problem is that because of the flexibility, matrices have been implemented in Stan so that it's matrix of variables, and so that order-diff, so when we have, oops, try to make it more straight. The matrices have elements. Each element is a node in order-diff tree. So this is flexible because then we can have assignments where we can assign certain element of the matrix value we want, and like each element can be assigned differently. But then it also makes it that we quickly have this n-squared memory cost in order-diff tree and building the tree. While if we know that this matrix is actually constructed from data, so we would have n-squared or n data points, and then constructing the kind of the data part would be n-squared operation, but then it's fixed, and then we have only few hyperparameters affecting covariance matrix, and then we should then use actually just one node for each matrix. And this is coming soon, so soon GPs are going to be faster in Stan. Sparse matrices are coming after that, and then we are recommending in many cases, instead of using GPs, using Markov random fields, and if someone wants to use in those cases specific covariance function, then we would recommend to go like the similar route as INLA. We have a work in process, Laplace integration over the latents. It's more suitable for something like Stan than variational inference. And then we get kind of similar advantage as in the INLA software. And then specifically, we've also looked at, we need to do the order-diff differently when we have a lot of hyperparameters, and that's then the part where, so I mentioned earlier that I mentioned before the talk started, if you listened my answer to Mike, that INLA software has a limitation like up to 15 hyperparameters. And then in Stan, using the Laplace integration, we can have thousands of hyperparameters with MCMC, but then that required, again, rethinking how to do the order-diff. So yeah, order-diff being automatic means that like here, PhD student did years worth of work and was able to publish it in NeurIPS type of auto diff. And even with these things that are coming, Stan or other generic people frameworks, they are not competing with specialized software. So there's a place for these special software, and I know like GPFlow can handle much bigger data and has flexibility to go also in interesting models, and even if not have the same flexibility, but then having a speed for big data. Okay, to conclude, very unlikely that one software would be best for everything. And when thinking as a user, which software to use, it's good to understand these trade-offs. As a developer, it's good to understand that maybe you should not try to have everything, or if you want to have more, you may need to do compromises. One good thing is that overall modularity in an interoperability of different software packages and these libraries is improving all the time. Examples are like this. What is this backend engine doing the computation? So for example, if you want to use GPUs, TPUs, that they are different possible backends, and it's getting easier to switch between backends. These probabilistic programming languages are having already transpilers, so that like when writing a model with Stan language, it's possible to also transpile that to Pyro and TensorFlow probability. So it's also possible that like if you used to use one of these languages and then have been making initial experiments with one backend, and then you could use in the end other backend to get additional speed, which may need then additional work also then to get it actually working that with that other backend. Julia seems interesting in the how the these different Julia packages seem to be interoperating better with each other than like in Python. And so overall, excited to see how this will also help like the GP software to develop to be more flexible.